Okay, so today's lab is oxidation and reduction. This is a lab where you have to be very attentive towards what's going on in each of the chemical reactions. And I really want to make sure we're all clear on how to assign oxidizing and reducing agents and how to count electrons, so that way your reports are cogent. So first and foremost, let's define the oxidizing and reducing agent. So when we say something is an oxidizing agent, what exactly do we mean by that? So an oxidizing agent is the species that gains electrons, And when a species gains electrons, so when you think the phrase gains electrons, what I want you to think, when something gains electrons, it's considered reduced. Okay? So this is the nomenclature that we're going to use for oxidation and reduction reactions. As a counterpoint, a reducing agent is a species that loses electrons. Okay, so the reducing agent loses or gives electrons. When we say something loses electrons, quite simply, it is quote unquote oxidized. Okay, so this is the nomenclature that we're going to use in this chapter to describe oxidizing and reducing agents. Now, how do we assess whether something gained or lost electrons? Well, the oxidation number, the best way I like to think of oxidation number as you calculated it in dry lab 2B, the oxidation number is the theoretical charge of an atom, assuming all bonds were ionic. Okay, so let's do some analogies. For example, PbO2 or lead oxide. I'm avoiding specifying the charge for now because that's an exercise that we have to do. So if we want to figure out the charge of lead oxide, how do you figure out the charge from the formula? Do we know how to get the charge from the formula? Yeah, so we take our subscripts and what do we do? Cross them. Yep, exactly right. So we take each of our subscripts and we cross them up. So that gives us Pb2 plus and O minus. Does this match reality? Does oxygen have a charge of -1? No. Oxygen ideally has a charge of -2. So we're going to need to multiply both of our charges by 2. Okay, and that in turn gives us Pb4 plus and O2 minus. Now, don't worry too much about when I'm writing oxidation number versus charges, why I put the plus sign in front for oxidation number and why I put the plus sign behind for charges. It's just implicit convention. Now, the key feature of this, we've assigned the charge of lead in this compound to be 4 plus, right? So if the oxidation number is the theoretical charge, assuming all bonds are ionic, what is the oxidation number of lead in this case? What's the oxidation number? What's the theoretical charge? +4, yeah. So our oxidation number is +4 for lead. What is the oxidation number for this oxygen? What's the theoretical charge of this oxygen, assuming all bonds were ionic, which they are in this case? What's the charge? Yep, -2. So we know how to calculate charge, right? And it's the exact same process to calculate oxidation number. Exactly the same, no modifications whatsoever. And to really demonstrate this idea, let's take a look at CO2. Okay, we're going to use the exact same process, except we know carbon dioxide isn't ionic. But if we want to figure out the oxidation number, we're going to pretend like it's ionic. Okay? So how do you figure out the charge from the formula? What do we do with our subscripts? Just like before, we cross them. Yep. Are we doing anything different? No, it's all the same. This gives us, whoops, it gives us carbon 2+ and O-. What do we have to multiply both of our charges by in order to get a charge for oxygen that matches periodic trends? 2. So we're going to multiply both of our charges by 2. That in turn gives us a theoretical charge for carbon is 4+ and oxygen 2-. Carbon is not an ionic compound, but for the purposes of calculating oxidation number, we'll pretend like it is. Okay? So what is the oxidation number of carbon in this case? What is the oxidation number of carbon? 4. Yep, or +4. And what's the oxidation number of oxygen? -2. Yep. Does this idea make sense to everyone? Is everyone comfortable calculating oxidation number or theoretical charge? For ionic compounds, the oxidation number is the same thing as the charge. Okay. So with that established, we now have a sense and we can start to describe chemical reactions. So one of the principal chemical reactions we're going to be looking at is known as a displacement reaction. So we're going to look at displacement reactions, okay? And quite simply, for displacement reactions, let's look at an example. So zinc solid can react with, for example, copper chloride in solution and generate zinc chloride and copper solid. Okay, so this is a textbook displacement reaction. So in a displacement reaction, we have on our left-hand side a pure element, okay? Our pure element zinc, okay? And this pure element zinc is reacting with a compound, and out of this chemical reaction, we get a new compound. And in addition, what do we call copper? Is copper a new pure element? Yeah. And if you look at this reaction really closely, fundamentally, what has happened? Has zinc replaced copper? Has zinc displaced copper? Yeah. So a displacement reaction is a reaction between a pure element and a compound to yield a new compound and a new pure element. Okay? Now, with that said, what we're going to do in this experiment is look at a series of displacement reactions. Look at a series of displacement reactions. And to make these a little more appropriate for the laboratory, let me change these all to the nitrate salts. Why am I changing all of these to the nitrate salts? Are the salts that you're handling in this experiment the nitrate salt? Yes or no? Why am I making this arbitrary decision? Are the salts that you're dealing with in this experiment for the displacement reactions that you're examining, are you looking at nitrate salts? Yes. So that's why I'm changing these to nitrate. Okay. Now, if we take a look at our oxidation numbers, we can see something quite interesting. So what is the charge of zinc as zinc solid? What's the charge of this pure element? Oh, no, just a pure element. Are there any charges written right now? 0. So the charge is 0. So I'm going to write a 0 up in front. Now, what's the charge of copper and copper nitrate? Let's just try to do this. Well, so taking a look at copper and then nitrate, if we have two nitrates and we cross our charges, what theoretical charge for copper do we get? Yeah, so we get Cu2+. So what's the oxidation number of copper? 2+, exactly. We're just reading off the charges, okay? Does everyone make sense? Does it make sense where I got these numbers from? Okay, so what is the oxidation number? What is the charge of zinc? In this compound, what's the charge? Yeah, +2 by the exact same logic as the copper nitrate. And what's the oxidation number of elemental copper? 0. Okay. Now, in essence, what we're now going to do is write a series of what are known as half reactions. So half reactions are separated into two major types. The first type of half reaction is oxidation. So we're going to look at what species is losing electrons. What species is losing electrons or your oxidation number increases. So what species in this chemical reaction, what species, if we compare the left and the right-hand side, has lost electrons? Has its oxidation number become more positive? Which of these species has the oxidation number, as we go from reactants to products, has our oxidation number become more positive? Zinc, exactly. So if we take a look at zinc, fundamentally, we went from zinc 0 to zinc 2+. Okay, now if we go from an oxidation number of 0 to +2, how many electrons have we lost? If our charge is conserved, if our total charge is conserved, we went from 0 to +2. This +2 tells us we have how many less electrons? How many less electrons when we have a +2 charge? 2. So then, how many electrons have we lost if we went from 0 to +2? 2. Now, there are two ways of thinking about balancing these equations. The first of which you can say the total charge on the left and the total charge on the right must be equal, right? So if we add up +2 and -2, we get 0. That's one way of thinking about it. The other way of thinking about it is that the number of electrons on the right are equal to your oxidation number for your product minus the oxidation number for your reactant. So this is one way of thinking about it. And our number of electrons is always going to be greater than 0. If you get a negative number, then you have to put the electrons on the opposite side. Does that make sense to everyone? The two potential methods? Okay. Now, the second half reaction that we're going to look at, number 2, is known as the reduction half reaction. So we're thinking about what species gains electrons. So in this case, what species is gaining the electrons? Copper, yep, it's going from +2 to 0. So for copper, copper is going from, you're starting with copper 2+ and you're ending up with copper solid. So if we're keeping count of our oxidation numbers, we have a +2 oxidation number going to an oxidation number of 0. So my question to all of you is, so how many electrons have we gained? If we went from +2 to 0, to balance out this +2 charge on the left, how many electrons do we need to have on the left? 2. Exactly right. So this is known as balancing via the charge method. If you want to count electrons for your reduction half reaction, the number of electrons on the left are equal to the oxidation number of our reactant minus the oxidation number of our product. And again, your number of electrons is always going to be greater than 0. So these are two methods of thinking about counting electrons for your oxidation and reduction half reaction. Now, as we notice, looking at each of these half reactions, what is the same in both of these reactions? What is the same in both of these reactions? What do you notice is exactly the same? What was that? The nitrate, yeah, sure. But looking at these half reactions in particular, the number of nitrates is important as it's an indicator of something, but what is exactly identical? What did we mention in class when we discussed redox reactions? What is conserved? What is the same in both our reactant and product side? What is exactly the same? The number of electrons, yes. Does everyone notice how we have 2 electrons gained and 2 electrons lost? So our net number of electrons gained and lost is 0. So we have the same number of electrons lost by our reducing agent as gained by our oxidizing agent. Okay. So the oxidation half reaction describes, so zinc, since it's losing electrons, what do we call the species that loses electrons, that gives electrons? It's oxidized, but what do we say? The species that gives electrons, what do we call it? Reducing agent. So this is our reducing agent. Okay. Copper is gaining electrons, taking electrons. What do we call the species that gains electrons? Oxidizing agent. Exactly. Okay. Does that make sense to everyone? How to dissect a reaction and identify your oxidizing and reducing agent. This is part of what you're going to be doing today. You're going to be writing off these half reactions. And all you're doing is just looking at your chemical equation and looking at the charge or theoretical charge at the start and at the end of your reaction. And from there, you look what oxidation number changes, what species has the oxidation number increase, the species that's oxidized, and what species has its oxidation number decrease, the species that's reduced. We write out the half reactions, and we make sure our electrons gained and lost in each of these reactions are the same. Okay, wonderful. Now, what is the point of all this? So what is the point of all this? Well, this next idea is going to be critically important, and it's this idea of activity. So you're going to need to find in your book appendix or in your book appendix online or in the chapter 7 notes, you will see something titled the activity series, So let's take a moment and let's go to the back of our lab manual and let's try to find the activity series provided. Let's just check to see if there's an activity series provided in the back of your lab manual. Let's check the front. Let me pull up one from the notes just so that way we can take a look at an activity series and talk about how to analyze it. Allow me one moment to pull it up from the notes. You'll need to have access to an activity series, or we'll at least be able to talk about the activity series, since part of this laboratory is generating your own activity series. Allow me one moment to pull up a copy for us to look at. And if you have your OpenStax book, there should be an activity series in the appendix of the OpenStax book. Allow me 1 second, I'm just pulling up the page. And if you have a copy of your book, that would also be a good place to look. Give me 1 second while the file is downloading, and I'll pull up, and then we'll talk about how to analyze an activity series, because this is integral to understanding how this lab functions and what you're going to be doing today. Any questions so far while we're waiting? Any questions so far on this experiment and aspects of this experiment? One moment, I just found the activity series. Let me just copy and paste it so we can all see it in the notes. Okay, can everyone see the table that I pulled up titled Activity Series? Okay, so this is your goal in this experiment. Your goal in this experiment is to generate an activity series. Now let's talk a little bit about what does an activity series mean, what does it do, and what's the purpose behind it. So for our activity series, so the activity series, quite simply, it ranks species by their reactivity in this case as reducing agents, Okay, so we're looking at the reactivity of species as reducing agents. So to give you an example of how this works, let's consider the case where we take our metal samples and react it with HCl. Okay, let's now talk a little bit about this. What metals are we reacting with hydrochloric acid? What metals are we reacting in this experiment with hydrochloric acid? This is really important. What metals are we reacting with acid? What metals are we reacting with hydrochloric acid? There's a list. Yep, nickel, copper, zinc, okay, iron, yep, aluminum, yep, aluminum, magnesium, etc. Okay, so let's just take a look at these examples. Now, you're going to observe the results of each of these reactions. And let's suppose that nickel, zinc, and iron, you observe a clear reaction. You observe bubbles, okay? So you observe a reaction and you see the presence of hydrogen gas, okay? When you mix copper with acid, you see no reaction, okay? This data that you've collected, whether you observe a reaction or do not observe a reaction, tells you how to place each of these species on the activity series. So the rule for the activity series, and we'll write this on the side of the activity series, is quite simply, you're going to identify and write your metal or your reducing agent. So in this case, right here. Okay. So in this experiment, depending on whether you observe or do not observe a reaction, the first step is to write your metal or reducing agent. So for example, we have nickel, iron, copper, etc. Okay. Then what you're going to do is if you observe a reaction. So first, if you observe a reaction, you're going to draw an arrow pointing down to your oxidizing agent. Okay, so when we react each of these metals with hydrochloric acid, what is our oxidizing agent? What species is gaining our electrons? So if our metal's the reducing agent, what's the oxidizing agent going to be? HCl, more specifically H+. And you see H+ in this activity series. So in this case, since we know iron reacts with HCl, we're going to draw an arrow going down, pointing to H+, okay? So our arrow's pointing down to our H+. And now we can write out the rest of our equation for this half reaction. Okay. So what this relative placement is telling us, what this downward arrow is telling us, is that iron is more reactive than H2 as a reducing agent. In other words, iron and H+ can react. Does that make sense? So from the fact we observe a reaction, we put iron above H+ on our activity series. Does that make sense? You draw your arrow down. Now, in our second case, let's say what happens if we see no reaction. So no reaction, you draw an arrow from your reducing agent pointing up to the oxidizing agent. In other words, for example, we said in our reaction screen, copper does not react. So we're going to draw our arrow pointing up from copper to H+. Okay? So as a consequence of this, when we observe no reaction, copper is below H2 and as a result is a weaker reducing agent. Okay. So the reason why we have you run so many different reactions is because you're comparing the relative reactivity of each metal and metal ion. So to give you an example, suppose we take nickel solid and we mix it with iron, a solution containing iron 2+. And let's suppose we see a reaction. By this logic, if I compare the relative positions of nickel and iron 2+, if I see a reaction, should my arrow be pointing up or down? Down. So then I'm going to circle nickel, and I'm going to draw an arrow pointing down from nickel to iron. So what species is more reactive as a reducing agent? What species is higher on our activity series? We see a reaction, so what's higher, nickel or iron? Nickel. Does that make sense to everyone? Now, and this is where we can really start to expand this idea a little bit further. This is where we can really start to elaborate on this. If nickel reacts with iron 2+, let's try to predict, let's try to see what happens if we mix nickel 2+ and iron solid. Would we expect a reaction to occur? And the way that we answer this question, quite simply, is we draw an arrow going from iron to nickel 2+. And my question to all of you is nickel 2+ higher or lower on the activity series? Higher, right? Is our arrow pointing up or down? From iron to nickel? From left to right? Up. So then, if our arrow is pointing up, what can we conclude? Would we expect a reaction to occur if our arrow is pointing up? No. So we'd expect no reaction to occur. So based on whether you see a reaction or a no reaction, you can place your metal relative to your metal ion. And that's what you'll be doing today. Does that make sense? So just to go through this example again, I ran these 4 reactions and I got these 4 pieces of data. Basically, whether I saw a reaction or whether I didn't. Okay? From these pieces of data, I can rank. If I see a reaction, I draw an arrow going from my metal to my cation pointing down. So iron reacts with H+, so the arrow is pointing down. If I do not see a reaction, I draw an arrow from my reducing agent, from my metal to my ion, pointing up. So in this case, we know copper does not react with HCl. So the copper is below H+. Does that make sense? Okay. So that's all you're doing today. You're mixing different metals and metal ions, and then based on whether you observe or do not observe a reaction, you place those compounds relative to each other on the activity series. The most reactive compound, the most reactive metal will be at the top. So in this case, nickel is our most reactive reducing agent. Likewise, copper 2+ is our most reactive ion. So this is our most reactive oxidizing agent. And that is what you're doing today. So you need to make sure you're carefully watching each of your reactions for presence of solid, color changes, evolution of gas. And from those data, from those observations, you'll be able to conclude whether a reaction has occurred. And if a reaction occurs, you can then place your metal and your ion relative to each other on the activity series. Does that make sense to everyone? Okay. So this is a 2-day lab, but I want you to at least get through the acid reactivity and the reactivity with nickel 2+ ion today. Beyond that, if you don't have any other questions, you're welcome to begin the laboratory. Please make sure you are mixing the correct solutions together. And if you have any questions, please ask me, your instructor. Don't just ask your lab mates, because if you mix the wrong solutions, it can cause some problems in this laboratory. Otherwise, you're welcome to put on your goggles and begin the lab.